let's get started. This is pretty. Let's start with the easy topic. Excuse me. Let's start with the easy topic first. Okay. Let's start with the key question. What is search? Anyone? So search, if you look at the dictionary, it means that you're looking for something, right? Looking for something that you want. Or, I think some of you may answer me with this answer. That means search is Google, right? So we are not looking at Google in particular, right? First, Google is a search engine. Okay. Now, how does search and intelligence, how are they related? So one of the major goals of AI, artificial intelligence, is to help humans in solving complex tasks, right? So we're not interested to look at simple problems because then you do not need artificial intelligence, right, to help you to do that. For example, this is a list of the questions that you, or complex tasks that you may want to get some sort of machine intelligence to. Can anyone tell me? There's one person who wants to come in. I think his name is Dyer. Is it? Anyone knows who is Dyer? This one looks a bit new. I think just a reminder: do not use your personal account to enter this Google Classroom. It will only recognize your IEC Gmail, right? Otherwise, you will get up. You can't come in. So please tell your friends or those who actually maybe cannot come in, especially those who cannot come in, to actually change to their IEC Gmail. No? Let me continue. So the first question will be, how can I fill my container with pellets, right? Pellets, you know, basically container is a big sort of box, I would say so, a container. How we fill it? So how can you fill that to maximize so that you don't waste a lot of empty space with a lot of space inside? What is the shortest way from Milan to Innsbruck? Now this one actually you will look at it and see that this is something that I would want to ask my Waze software to let me travel from A point A to point B. Now the reverse of shortest way would be, I think you all know, those of you who stay in the big cities, you know that shortest way may not be the fastest way. Right? From point A to point B is the short. However, due to traffic jams, things like that, it may not be the shortest. So sometimes it might take the longer way in order to reach the destination fastest. So the third question will be example of why AI can be helping humans to solve complex tasks. Will be what's the fastest way from Milan to Innsbruck? And then this one is how can I optimize? This one is also related to, similar to the first question here. How can I optimize the load on my freight to maximize my revenue? So what does it mean? It means that I want to pack the most number of things inside my box so that I can, because when you pack things inside a box, you're helping people to ship things. So the more you can pack in, the more revenue you can, on income that you can generate. Another example would be how can I solve my Sudoku game? So this one, I think you look at it similar to games like this Go or the checkers or chess. You know, you can just program it so that. Now, why do you do that? Because when you are able to program using AI to help you to sort of play the game, you can also maybe later on sell it as a game to the public. So that's one example of gaming. So actually, for those of you who are aware, gaming is also a big industry. I think they also need lots of people to help them to program things like that. Now, by the way, I'm also reminded of this morning. I saw the papers. There was one full page of the, most of you who have the Star newspaper, go and check it out. There's a whole page of advertisement from San Dadi, I think plantation. They're looking for a long list of robotics engineers. Now, for E&E students or even the telecommunication students here, will not worry, because I think many of the things that in robotics you can also maybe apply, because your actually E&E is actually quite flexible, especially if you're majoring in electronics. So we'll check it out, the whole front page. So you can see here, especially with the lockdown of the MCO and with this pandemic happening around the world, not just Malaysia alone, you find that things have changed. So they're looking for a lot of this technology to help industry to solve their problems. And then, especially in Malaysia, whereby we cannot, we are discouraged from hiring cheap foreign labor with low skills. Of course, if you have high skills, I think Malaysia still wants you. But if your skill set is not so high, so Malaysia would not want to let you in to give you a permit. So the next one is what's the sequence of actions that you apply to win a game. So you can see from these two examples here, from in the gaming industry, right? You have there's a great need for artificial intelligence to actually program or develop the engine to play the game. Now, sometimes finding a solution is not enough. You want, because finding a solution can be quite easy, but of course you want you try to want a better answer. So you want the optimal solution according to some cost criteria. So you have to again back to our discussion. I think last week we talked about measurement. So I can give you an answer to your problem, but you still need to know how good is that problem. So it comes down to, again, measurement. Now, all the example presented above involve looking for a plan. And you have a plan. What is the from Milan to Innsbruck, fastest way from Milan to Innsbruck, shortest way from Milan to Innsbruck, how do you optimize the load for your freight to maximize your value. So in this case, it's straightforward. In the case, so the cost criteria is you pack as much as you can and fit into that. So this one actually is, look at it simply, it will be probably two criteria. What are the two criteria? The first criteria is you want to, there's a certain constraint in terms of space. You cannot fit, so that all the load have to fit inside that container, the freight, the box. And of course, if you pay more, for example, you pay more for your, maybe the weight also of your cargo of your goods is heavier. Also, you have to worry because the freight also, maybe there's a limit to the total weight of inside the goods inside the box of the freight. So all this is about some cost, right? You still have to look at the measurement of what is the solution, right? So solution A, you have 10 boxes, and then you find that the total weight is X, and also the revenue, how much you charge your customer, come to some numbers. But in another example, the same box again, the same container, maybe now 20 boxes, 20 goods, 20 boxes of goods, and then now the weight is although it's lighter, right? But of course, because you're now able to pack 20 boxes into your container, you can get more money, profits from your customer. So all these examples presented above involve looking for plan. Now, the plan that can be defined as a set of operations to be performed up of an initial stage to reach the final stage, and that's considered the goal stage. So again, what's the plan for packing in things? So once you have the plan, you can then program it according to the plan using artificial intelligence or AI. So therefore, we need efficient techniques to search for the path, to search for certain sequences. Because you look at it here, you have an initial state, the container is empty, and you want to pack as much as possible into your container. So that is your goal state or final state. So you need to find the techniques, the steps involved to search for path, right, or sequences of actions that can enable us to reach the goal state, that is to find the plan. Now, such techniques are commonly known as search methods. In case I need to change it. Okay, now continuing, many people believe that all AI is about search. So that's why it's very important. So AI is all about search. You have to search for certain sequences, certain steps, and certain solutions. And looking at it, things like game theory and also problem spaces. What is a problem space? You're trying to look for the answer, right? So you have to define, be very clear about your problem space. Now, every problem is a feature space of all possible, either successful or unsuccessful solutions, right? So if you're given a certain problem, right, you know that you have to look for the answer within that problem, within that problem space or feature space. Now, what do you mean by feature space? Let's go back to the example of the freight, packing things as much as possible into your freight container. So you have to look at the problem space, right? How many things can you pack inside? So it's one feature in terms of number of small boxes. The second one is maybe the total weight of your boxes, and then there can be what do you call that? The next one will be in terms of the cost. How much is the customer paying for that box? For them to for you to ship ship their things for them, things like that. Of course, you can put in only one box, right? So they'll be still okay, right? Or you can be unsuccessful in the sense that you cannot fit now the box into that particular container of freight. All right. So okay. So the trick now is the trick or the answer is to find an efficient search strategy. An important aspect of intelligence is goal-based problem solving. So what does it mean? It means that you must be driven. The answer, the solution must be driven by where is your destination, where's your goal. Right? So let's see here. Okay, very well. So the solution of many problems, for example, the game of knots and crosses. I think many of us have played the game before, right? Timetabling. How do you find the best timetable so that you don't have to, especially in the old days? Yes, I did. Don't see. I posted this part of it. There will be additional, additional material. This is an incentive for you to attend the classes and not just rely on the one I posted. Correct. I think this is week 2, isn't it? Week 2. I think it's more of topic 2. I think I posted. Is it correct? Is it? Yes, correct. Because it's supposed to be I think additional material for you. So I think give you an incentive to come to class. At least you see things a bit additional notes for you to. I pretty expanded the notes so that it's better. You maybe understand better. Let me continue. Come back to here and continue. Okay, where am I? Okay, here. Now the solution for these problems. Let's call this problem the timetabling. Back to the example of timetable, right? For example, in the old days, when you have to physically come to class, hopefully it will happen again very soon and not too far away, not too in the far distance. Means that one class in the morning, like now, 8 to 10, and then the next class is 5 to 6, for example, right? So the whole day you have to stay in the campus. Some of you find it a bit tiring to stay in the campus. So obviously, the best timetable will be everything packed back to back, right? So that you finish everything within the say space of 4 hours by 12 o'clock. If all your lectures finish, and then you're going to rush, right? Imagine if your class is in block M, then your next class is in block S, SQ, is it? SQ in the East Campus. So you have to rush from the main campus in the West Campus to the East Campus, and then the next class starts immediately after the previous class. Like now, this morning we have this research methodology workshop conducted by Dr. Hadi. I think you all should be attending, right? You all should have attended. So imagine in Dr. Hadi's class is in FG because many of you are combining the mechanical students, mechanical engineering students, combining the mechatronics engineering students, and also the ENG students, right? So you need a big venue. So the venue that can be sufficient to house all the students also has been considered. There's another feature for you to look at. So that feature space will have all these things, right? So so it's not so timetabling, although it seems simple, can be a very challenging problem, right? Because to get you the best answer, right? Of course, you can simply put in, right? Humans sit there and just simply assign the students and the venue, right? And the time, three things, right? The capacity of the venue, the number of students, what else? The time slot, right? And whether you have the class or not. So it can be quite complicated as the number of features expands, grows. So the best thing would be to find a timetable that is enough and doesn't clash. That's also the other thing. It clashes with your other papers you are taking. Some students might take paper A, some students might take paper B, and you cannot have student A and student B at the same time because their classes will clash. To consider those things. And so of course chess. I think you add that to the list here will be things like new game will be like Go, right? And of course maybe even things like Chinese chess, those other games. So the solution to many of these problem examples can be described by finding a sequence of actions that lead to a desirable goal. The goal is to win. In the case of a game, of a chess game, you beat the other, beat the opponent, right? You beat the other player. Timetabling movie, everyone is happy. There's no clashes of venue. The venue can accommodate all of you. Imagine if I squeeze everyone here into, let's say, there should be 90 of you. Into I see only about 84, 86 of you. I'm not able to make it this morning. Imagine I squeeze all of you into block M, one of the classrooms here, which can at best fit about say 50. Right? Imagine all of you squeezing into that room. So of course it's not a good answer, right? I won't call this an intelligent solution. Furthermore, each action change the state, and the aim is to find the sequence of actions and states that lead from the initial state to a final goal. It will change. Once you do a certain thing onto the current state, it will change the state, right? Because now it's moving towards your goal. I think it becomes clearer when we look at the example on the next few slides. Okay, so just to summarize, right? To summarize it, the well-defined problem that can use search to find the answer can be defined by these 6 different states, right? Or let's look at them one by one. So in the first one, of course, obviously it is the initial state. What is the starting point of your problem, right? So if you look at the example of the finding the fastest way from Milan to Innsbruck, as we have discussed in the earlier slide. So what is the shortest path from Milan to Innsbruck? So you need to know that whether you already know that your initial starting point is Milan, but your final destination is Innsbruck, right? So this is you know 2 of them, right? So you know that initial state is Milan, and then as you proceed from Milan, moving towards your destination, which is Innsbruck, you need to check. So you need to have a goal test. These 2 things. Okay, let me try to do this. Okay, so we have this and we have this done, right? So of course, then you also need to have an operator or successor function. How do you move from initial state to the next state, right? So the operator or successor function is for any state x, you return the function, it returns a value s of x, which is a set of states reachable from x with any one action. So what this means is that from point A, from Milan, right? There's no the next state cannot be KL Kuala Lumpur because it's not practical. So you need to know which are the immediate possible solutions for the current state. So from Milan, what are the next states available to you to that system, to that AI? So state space, the third one is the state space. So state space is all the states reachable. So this is a function of how do you move that from the initial state. So this one actually the state space. All the states reachable from the initial by any sequence of actions. So, okay, traveling by car will be different from, okay, if you're traveling by, say, plane or motorbike or bicycle. Right? So this is so we have this available. Or maybe even in the case, a good example would be if you're looking at this traveling Milan, right? There's no road leading from Milan to, I don't know, I'm not familiar with Italy. So another town, because the one is across a river. Unless there's a bridge there, so that next point, next neighboring city or neighboring town cannot be reached from the current state, from the current town. And path. So this is the actual path. So say let's not try Italy. Let's try KL. Right? I want to go from KL to Penang. Right. So my destination is Penang. My initial state is my initial starting point. Or the starting point is Kuala Lumpur. So this one I need to then from once I'm able to reach, right? I'm able to reach. Oh, sorry, I'm able to reach Penang, I'll reach the goal state. But so then what is the optimal path for me to go from KL to Penang? That will form your solution for the path. Now that path you need to be able to measure. Right? Remember, you still come back to what we discussed earlier. We need to be able to measure what is the path cost. Right? So if I find this solution, for example, I go from Kuala Lumpur, what's the next town I should go in order to go to Penang? Can I go to Surabaya as my next city? Yes, I can, right? Although it doesn't make sense as a human, as a person, right? Because why are you going to the south when you want to head towards Penang, which is to the north of Kuala Lumpur? So, if I do decide to take the next town to visit is Surabaya before I end up in say Surabaya, maybe go to Kuantan. Kuantan, I maybe go to Ipoh. Ipoh, I come back to Pry, right? And then I keep Penang. So that's the one solution. That one will give me I can measure the path cost. If I were to take that particular sequence of town to visit, to go, I can still arrive in Penang. So that is a good solution to have, but it's not the best because your total cost will be quite high. Right, so some is actually, so you need to have a function that measures that if I travel to this path, what is my cost? So you will be able to measure, right, the same thing. Or I think many of you are doing FIP, so you need to also measure your solution that is generated by your system. Now, in this example, the cost of a path is the sum of cost of individual actions along the path. So from KL to Surabaya, what's the total distance, maybe in terms of time, in terms of petrol the car will use up, for example. And the last one is actually the goal test. So if we go from KL, next to modify the move from KL to Surabaya, that is the operator to move it from KL to Surabaya. Then you look at the path cost. If I move, and then you look, then of course every step you move, you need to check. Are we there yet? Have we reached Penang? Right? KL, Surabaya. Is Surabaya Penang? It's not, right? So you can from Surabaya, you move to the next one. You choose the next step. Maybe in this example, you say it's Kuantan. Kuantan, you say is Kuantan is the next step. Is it the shortest one? Actually, is it the Penang? No, and you want to get right. That's how it goes. This one will be again discussed further in the next few slides. Right? Any questions so far? So, what do you hope to learn from this topic number 2? Right? Week 2. Right? So, at the end of this lecture or the topic, you will have understood some of the problem-solving agents. We also will look at how do you formulate a problem, right? So the problem, and then we will look at several examples of problems that we want to solve, and this is actually modeled as a search problem. And then we look at some of the simpler or basic search algorithms that we can use to find reasonably good answers to problem that we want to solve. Lastly, we look at one case study, which is a traveling salesperson or commonly known as TSP. Which is, although it's simple enough, we find that there actually currently there's no method, especially using AI, to actually find the answer to this problem. So this is the sort of the pseudocode for a problem-solving agent, right? So this one I think actually summarizes the earlier discussion we have about we need to identify the user state, and then need to update the current state with the new state, and then you keep checking, are we there yet? Are we reached the goal? So this is sort of the general outline of the pseudocode for the problem-solving agent. Now, let's look at one example, whereby a simple example to illustrate, to actually explain this search. Now, this is a very simple problem, which actually we call it the vacuum work from the eyes of a vacuum cleaner. So, it's a simple fictional word, very simple. Now, it contains just two squares, left and right. If you can imagine, the vacuum cleaner can be either in the left square or the right square. The vacuum cleaner will sense, will also detect, will know what the square it is in, know its surroundings, where am I, and whether there's any dirt. Because as you know, vacuum cleaner's role is to make sure the floor is clean. So therefore, it must know where it is, and it will be able to check, able to find out whether there's any dirt on the floor for it to do something. So the vacuum cleaner, in this example, can only perform two things. It can move to the left, if it's on the right, if it's on the right, it move to the left. And then that it can also detect. There's a sensor that will detect is the floor where you are now standing on or placed. Is there any dirt? So there's a detector to detect. Now, if there's a dirt there, you will perform an action called sucking. You will suck up all the dirt, remove all the dirt. So basically, three things. You can move, you can also sense the dirt, and it can perform the cleaning action, which is to removing the dirt on the floor. It consists of a vacuum cleaner. If this is an intelligent vacuum cleaner, it will have a few simple rules. Now, the first rule is, if the current square is dirty, then you remove it by sucking up. Right? Vacuum will remove all the dirt into the bag of the vacuum cleaner. Otherwise, if the current square is clean, you then move to the next square. So you move to that from clean or clean already to the next one and check, do the same thing again. So this is obviously the rules governing the action of this simple intelligent agent called vacuum cleaner. So far so good? Now, this is a visualization of our vacuum work. Now, this actually now just for two simple squares and dirt. So it consists of in the physical world the world is only two squares. The world is actually have dirt. Now, based on that, you find that there are 8 possibilities. What does it mean? It means that let's start at the one here. If the vacuum cleaner is sitting on the right square, and both squares are clean, right? Now, if you look at it again, you can see that I can also generate another possibility or combination. That is, the square that the vacuum cleaner is sitting on, which is the right square. Now, the right square, first one is clean. The second one is dirty. So now I have two possibilities, right? And then the list goes up. So this one is the right hand side is clean, no dirt, but the left hand side is dirty. Now another one is the right hand side is dirty, and so is the left hand side of the two squares. So both squares are dirty, but the vacuum cleaner is sitting on the right hand side. These four of them can also be mirrored, can be duplicated, repeated on the left square. So left squares both are clean, but the vacuum cleaner is sitting on the agent. The cleaning agent is sitting on the left side, and it goes on. So we can have 8 possibilities. That's on this simple example of whether clean or not, and whether it's sitting on the left or sitting on the right square. And then, if you remember, we talked about this before. There must be 6 key points for the well-defined problem. So we start with, to solve this problem, you must know where is it starting. So for example, if you see that we're starting at this space here. You're starting here. What is your destination? That means what is your goal? Your goal will be make sure that both are clean, right? So you don't know yet. You only can sense dirt or not, and you know where you are, right? So you don't know the other combinations. Okay, so we can be even here, but we cannot see this, right? So we start from here, right? And see what happens. So we can also start from here. So we can define various kinds of starting point, which is your initial state. Right? So we start from 5, this example here, this initial state. So, so if you are on the then you will of course check, is my current cell, my current square, is it clean? If it's clean, then you move to the right hand side. Then of course you check again. Is it clean or dirty? If it's dirty, as in this example, in this particular starting point, you will do a sucking up the remove all the dirt, right? You can also start now for this starting in few of them actually. So if you start from right hand side, right, you can only go to this is your world, right? So you can actually you can't go up. There's no up. No? So you're sitting on the left hand side. You can only go to the right hand side. The right hand side, there are various possibilities. So that's why you have possibility put number 2, which is right hand side is dirty, that's where you are. And then of course you can also have this state, right? By moving to the right. Can I? So this is out because right, you know that there's no dirt here, so this is actually out. So we can have only these 3 actually, right? Because it's if we have move to the right, and this is actually similar to this, right? And so this is actually, there's also no dirt here. Both sides are no dirt. But in this case, we have dirt. We know that this is a starting point, so this should be actually this one, right? So of course, some of these are not possible, so you have to decide, checking out, and move to the right hand side. So we have you go to the right. Actually, possible solution is you go to the right, and then you clean up the dirt over here. So you can then come back to the left and then clean up again. Now, what we call contingency. What does it mean? It means that sometimes because your vacuum cleaner is not working perfectly, by sucking up the dirt, it can also dirty the already clean carpet, because for some reason you actually not only are you sucking, you're actually blowing up the dirt on that, right? Partially observable means that you can look at you are able to know, right, the location where you're in, and also the dirt at the current location. You can check, right? You can check, so you can observe. The agent, the vacuum cleaner agent can observe, right? Partially observable whether there's any dirt at your current location. So we can also depend on your starting point, which is start at 5 or start at 7, right? So there are 2 possibilities, right? Because as far as you're concerned, if you're sitting in these 2 are the same, right? Because these 2 are the same in the sense that this particular square do not have any dirt. So these are 2 of the possibilities. Now you move to the other side here. The possibility is that it can have dirt or can also have no dirt. So this one we don't know until we move to the right hand side. you can see all the possible possibilities you can have. This one actually expanding that. Right? So now this one actually, so the solution is if you move to the right. So move to the right, then think of it as a sequence, as a flow chart. You move to the right, if it's dirty, you need to check. Use your sensor to check. The vacuum cleaner agent will check. Is it dirty? If it's dirty, then you move it by sucking up the dirt. So you can see now, once we've done that, you can see that we can actually build what you call state space graph or state space map. So in this example, if you say that if it's so we have a few things here. What is the state? What we do? Of course, at every point we have to check. Have we finished doing our job? What's our goal? What's our objective? And then the last one is that we have to each time we do it, we have to measure the solution cost. What is the cost of that solution? So let's look at this. I think some of you may recognize this as something we have done again in the finite state machines, right? You have so in this case we have two. In this example, we have two particular squares. So if it's dirty, it's sitting on the left hand side. If it's dirty, you remain behind and then you clean up. Or if this one is after cleaning it, then you also move to the next one, right? And move to the next one, move to the right, right? In this case, so we have move over here. Then if it's dirty, you clean it. This is clean. And then after that, you can also move back to this, right? You can see this is actually you built that, particularly the overall state space graph for the simple vacuum cleaner agent. And the same goes for the other side. If you have this scenario, right? Both of them, of course, both squares have dirt, but now the vacuum cleaner is sitting on the right hand side instead of sitting on the left hand side. That's what I mean, right? So we have two possible. These are all the possible states of your world, the simple world of your vacuum cleaner. Right, so if this is 30, so instead of sitting over here, now the vacuum cleaner is sitting over here. So depending where you start, so then you start plotting out the path. Right, after that, from the end, you can see towards the end now, all are clean. So so this is actually the state will be dirt will be yes or no. So it's an integer. Maybe for example, if it's 30, you put a 1, right? Integer of 1, a value of 1, and if it's clean, it's a value of 0. So yeah, that's how you measure the able to recognize, right? And then where is the location of my agent, my vacuum cleaner agent, right? And then the actions if I can move left or right, and then do a removal, sucking up all the dirt. Then you check, right? The goal is what, as I said before, the goal is make sure there's no dirt at all locations. And then how we measure the solution action, right? When you move, so you'll be maybe you assign a value of 1 for action by moving left to the right, right? And then you assign a value of 1. So up to you to select, but you have to assign a value, right? So of course, the best thing will be then what is it? This is a minimization problem. What it means is that you try to have the lowest cost by making sure you clean everything, right? So of course, this is a simple example, right? But if you expand this, scale this up to a larger problem, like now we have many squares, not just 2 of them. You find that depending on your plan, right, on your strategy, how your robot move, you can end up with a solution which is actually wasting time. Means they have a lot of high cost to arrive at the same solution of no dirt, versus another one which is the lowest cost and both the squares are all clean. So I think you can imagine that. Now let's look at another example that is easier and also at the same time a bit more complex to try to look at it from the point of view of a search problem. So this is an example of you're on holiday in a country called Romania. Okay, so this is your search space that is called Romania. And then your starting point, which is you are starting in a city called Arad. Now, then what is the problem you're trying to solve here, right? So you're trying to get the AI, the intelligent agent, to solve the problem for you. The problem is that you are currently in Romania and your plane, you are now finished your holiday and you want to go back to, say, Malaysia. And the only place you can fly back to Malaysia is actually a city called Bucharest. And of course, obviously, Arad is not the same as Bucharest. So you need to find a way where you are holidaying from Arad to find a way to reach the airport on time so that you can board the plane to fly back to Malaysia. Got it? So this is your example, like the problem you're trying to solve using artificial intelligence. So your goal is to find as quickly as possible find your way to the airport in Bucharest. So you have to figure out the problem. You need to figure out where are all the cities in the country called Bucharest. So this is the first one. And then since you are driving, right? So you have to decide how do you move from Arad to Bucharest. So suppose you drive. So the action is you're driving between the cities along the way to reach your destination of Bucharest airport. So the solution will be find this. How does the solution look like? The solution looks like this. You have to find a way, for example, from Arad to the next city, and then from the next city to the next city, and finally you arrive at your airport in the city called Bucharest. Right? That's again our example before. When we talk about Malaysia, we're trying to find a way from KL to Penang. Right? So for some reason, or maybe the other way to imitate the same problem, you're trying to find your way from you're flying to Korea, right? And there's no, although Penang has an airport, but the airport in Penang doesn't fly. The planes that land in Penang do not fly to Korea or Seoul. So as a result, you have to make your way either by bus, no, not by bus. The bus is you bought the bus and you don't have to worry about how you drive. But you're driving from Penang and you're not familiar with the country, right? And you need to find your way to Kuala Lumpur to catch the flight to Korea. How do you do that so that in the quickest possible time, right? And of course shortest possible time as well. Distance as well. Right? So this one is something that we know, we can see. This is actually not given in the sense that your agent doesn't have this map. It's not shown this map. It means that you can only see this. When it knows it's starting at this point. It knows that the neighbor I can go from Arad to this city, number one. And I know that there's another alternative. I can go to Sibiu, number two. And of course, I can go to a city called Timisoara, which is number three. It cannot know that I cannot go from here to here, to find the way. So it doesn't. It's only limited. You can only see this and not, further away. Right? This is what it means. You know, there's immediate neighbors in this example, right? And other thing it needs to know is that what's the distance from. So this is a measurement. If I take, so we have three choices. I can go from Arad, I can go to Zerin. From Arad, I can go to Sibiu. From Arad, I can go to Timisoara. Question then is, I have three choices. Which one do I take? Right? If I have 10 ringgit in my pocket, right? I want to have lunch. Can I have a pizza for less than 10 ringgit? Can I have say a chicken rice for less than 10 ringgit? Or can I have a nice what is more expensive than okay, maybe roti canai or less than 10 ringgit. There are three choices. So we have to, in this example, of course, it makes sense, isn't it, to find that. So I come back to what is my objective? Objective is my again, this is a fictional problem. Shortest distance obviously means that if you travel at the same speed, it will be faster to travel a shorter distance compared to a longer distance or further distance, right? So because I don't want to waste time from traveling to Iran to catch my flight in Bucharest, right? If I take the longer way, of course, take longer way means that I go something like this, right? And go this one like this, right? So it doesn't make sense. So your AI will tell you that the fastest way is from here, for example, like this. But later on, we find that the agent is not given such information. It cannot see beyond this small area. So we look at what we call the Presearch Algorithm, the tree structure, right? Now, what's the basic idea? The basic idea behind this Presearch algorithm is that it's basically offline. It will simulate it will explore what we call the state space. This is the whole space of possible solutions to your problem that you can solve. And this is the search space by generating successors of the already explored state. That means that basically also known as expanding upon the current state. So this is your fundamental or basic idea behind such a tree search algorithm. Now the tree search algorithm, as shown here on this little table here, it can return a solution or it also can return no solution or failure. Right? Come to the end. So you must always remember that the Presearch problem can result in a solution in which Bucharest, or it can result in failure. You fail to reach a state like this case. Let's say if the reverse is true, let's say we try this one here, right? If you are starting from this city called Vaslui, hopefully I pronounce it correctly. I want to also go to Bucharest. Now, if I use the same thinking as before, meaning that I want to find I will only take the nearest neighbor so that I hopefully, if the distance travel is less, I will reach Bucharest fastest. Now, as I said before, you can only see these two things here in front of you. I can see two neighbors. I have two choices. I can take nasi lemak, or I can take pizza. This example, a similar example. So, both have the same amount of food. Both of them I like, but this one costs more. This one costs less, right? So, of course, I'll pick the one with the cost a bit cheaper. So I take lassi. Now, after lassi, what do I have? I only have one choice. After taking roti canai, I can only take char kway teow, for example. So I will take this one. Now notice that if I do this, what happens? It results in a failure, right? Because I cannot. After this, I know that it is not the same as Bucharest, and then I know where to go. So this is failure. Right. So my Presearch algorithm can result in can return me a solution or return me a failure. Means that I cannot find you an answer. That is normally possible, such intelligent, so-called intelligent systems. So how do we start? We initialize the search tree, right, by using the initial state of the problem. This one I won't go through. You can read through it, but better for me to explain in the next few slides to show you how it works. Right? So I think I have time. I'll finish this before we stop. So we have, you can see here, this is my initial starting point, which is era. So from here, you can see that I have three neighbors. I only see these three cities where I can go. I'm given three choices. Like I said, I've only given either to take nasi lemak, I take chicken rice, or I take roti canai. So in this case, how do we select another additional point is that, as I said, the constraint is you will try to take the nearest neighbor. Right? This is what we call the nearest neighbor search. Right? So this is okay. So we have three neighbors. You can take Sibiu, you can take Timisoara, or you can take Zerin. Right? So we take Zerin because so we take Zerin here because let's see if I can erase this. Okay. Okay. Here. So you can see here from I have Zerin, I have Sibiu, I have Timisoara. Right? So if we take Zerin, sorry, we take Sibiu will be 140 versus 150. So this one for some reason is taking there. Oh, this no, this is just expanding. I just trying to expand it. So if you expand CBO, what are the neighbors for CBO? So basically, the search strategy is defined. We are now taking the order of the door expansion. So which one do you take? Right? If we take the shortest one, who's the shortest one, and then from there expand. So this one, if I take CBO, okay, this one doesn't expand by any choice. It just expands it. So this is the example. If I expand the node here called CBO, the city or called CBO, these are the neighbors. You can see here it's also repeated. Right? Obviously, it's still correct, or depending on your way you write your program, you can also say that it is the same before you invoke and take this. Right? Right. So the search strategy to find the path, the shortest path, so that I can arrive at my airport as soon as possible, fastest way, so that I have more time to visit Iran before I fly back to Malaysia. So I want to have the fastest way, fastest. I know that what's the fastest the path I should drive to arrive at the Bucharest airport in time to catch my flight. So this is actually defined by taking the order of node expansion. How do you select the next node, so on and so forth. Now, the strategies are each of the strategy. Which one do I take? Do I take CBU? Do I take Timisoara? Do I take Zerin? All this depends on few things here. For example, it depends on the completeness. If I take this way, if I take this point, the next node here, will it always find a solution if one exists? Right? So this is my strategy to select, to actually evaluate. Time complexity. What is if I take this particular strategy, what are the number of nodes generated? So again, you look at it closely, what does it show you? It shows you that again, the measure. We have strategy A, strategy B, based on completeness, based on time complexity, or based on all four of them. So if based on a few of them, does it always fulfill? If you take only this, does it fulfill a solution? If I take this strategy, if one exists. However, I can also look at the complexity. How much time do I need to generate the nodes? Is it faster if I do this way, or faster if I do the other way? Space complexity. Now, as the number of nodes increases, there's also what I call cost. You have to pay the price for storing the number of nodes in memory. Can I cope? Can my system cope? Right? So what is the maximum number of nodes of that particular strategy when it generates the nodes after each step? Optimality. Does it always find the best cost or least cost solution, or it doesn't? So we can measure each of this strategy, which will show in the next few slides, based on these four different examples of all different measurements of the strategy that we can adopt. This is something for you to just take note. Time and space complexity. Time and space complexity, these two here, are measured in terms of something called a factor called B, which is the maximum branching factor of the search tree. What is the number of what I call branches you can expand from the current node? What is the depth or D, what's the depth of this cost solution, and also what is the maximum depth of this space. Can be actually can be infinite, infinity. It can expand until you know come back, right? So it can be so we have to measure that so that we know that which strategy we should adopt, right? So that we will still reach answer, get our answer quickly, the best way. So in the next few slides for this lecture, we'll look at a few of these different search strategies. So let's look at the first one called uninformed. So it's uninformed search strategy. Use only the information available in the problem definition. So it doesn't have additional information. So it only has information given to it at that point in time. So the other one is actually one example would be breadth first search. So these are all examples of uninformed search strategies. So this is a breadth first. What it means, you look at it closely in the next few slides. Again, uniform cost search. That means that all the each step have a same cost. Right? So of course, you have more steps, it will cost you more. Right? Depth first search, and then refinement of the depth first will be depth limited. So we do not let you see later why we have this depth limited search rather than have a depth first. Of course, we can see that the depth first search actually has limitations, has some weaknesses. Therefore, it was proposed that instead of depth first, we have it constrained, we have it refined, improved with a depth limited search. So we do not let it go all the way just depth first. We limit it to a depth limited search. That's why it's called depth limited search. And then another one is called iterative. Again, refinement of this depth first. You can see, maybe it's obvious to some of you that because of the weaknesses of the depth first search, people have come up with two variations, two variants of depth first, which is depth limited and also iterative deepening search. Again, I will explain this in the next few slides for that. Now, another name for this uninformed search is called blind search, right? Basically, you cannot see beyond the information given to you, right? So it's also called blind search. Okay, maybe I'll stop here. So we come back tomorrow to go into breadth first search. This for us to explain and show you how it works. So we stop here. Are there any questions? Stop. Okay. If there are no questions, I may go for the next class. Brenda and Yao Ting, can you please stay back? I want to talk to you about your FYP.
Oh, by the way, sir, just a quick question. I was wondering, like for example, sometimes let's say this like for some other projects, sir. So like for example, if we want to optimize some stuff, right? Sometimes like you need like simple feedback loops, right? In order to optimize stuff for. Then where does it differentiate from AI? You know, like something that can be resolved with simple feedback loops versus something that can be resolved with AI. Hello, sir. Can you hear me? Never mind.
Oof, man, don't worry about it, dude.
No.